part about the multiple doses regimen of extravascular route of drug administration. And again, we will not go into the details of the this model or this dosing regimen. You will know some of the stuff that is related in a way or another of what you know for the IV bolus. So to make it easier on you to study it and just to understand the overall, let's say, concept out of it. Okay. If you remember, we know that from the single dose that we have on a this is not rectilinear, this is similog profile, okay, in which we have, if we are talking about one compartment, we have total two phases of absorption phase and elimination phase, okay, and again, because we had a lot of questions about it on the discussion form that is related to it, and under general conventional kinetic, we have absorption rate constant that is higher than the elimination rate constant. That's why the dominant here is absorption and the dominant here will be elimination, okay? But this is absorption and this is elimination or post-absorption phase, okay? So it's just different terms of the same thing, okay? Under conventional kinetic or the normal common case of kinetic, the absorption rate will be higher than the elimination rate in this phase. We will have the maximum, and then we will have elimination rate that is higher than the absorption phase. Okay. Then when we talked about the terminal was a special case of the elimination phase in which the absorption phase or the absorption rate is equal to 0, where we waited to reach the terminal phase to make sure that I only am talking about elimination, so we can determine the elimination rate constant, and we can by extrapolation determine the intercept, which is the overall constant that we have here. And again, this was our concentration equation here, in which we have the constant multiplied to two exponential term, which is by exponential term, one is related to elimination and one is related to absorption. Okay. From the what we know about the kinetic of extravascular 2, we know that we start at 0, right? We reach the maximum when the rate of absorption equals the rate of elimination, and at time infinity, we will reach what? 0 again. So 0, maximum, and 0. Okay? This is what we know from the already extravascular one compartment single dose. Okay, and this is what I just mentioned. We have the absorption phase, post-absorption phase, which again is related to when the elimination rate is higher than the absorption rate, and then only elimination and at the terminal phase. Okay, and I just talked about this. An extravascular multiple doses, the only thing that we need to take into consideration the multiple dosing regimen. And this happens by the same concept when we are talking about multiple doses in extravascular. We are talking about dependent multiple doses, which means that we have accumulation. And when you have accumulation, you have a build-up in the concentration until you reach a steady state. And we used in IV bolus the dust ratio, the same thing. We use dust ratio, but we will have one main difference here, that we are having one dust ratio that is related to elimination and one dust ratio that is related to absorption. And notice here we have K, and here we have K and K. Okay, so just the same equation that you know and the same concept that you know for IV bolus. The only thing that we are having two dust ratios because we have two exponential term. Okay, and the same thing, as you know, this is the nth dose, or the dose that I'm talking about, I'm interested in the time since the administration of the nth dose, and tau is the dosing interval of the dosing regimen. And as we said, n will be, again, as it's just a concept, n will be ranging from 1 to infinity, which means a single dose or a steady state concentration, and the time, which is again the time since the administration of nth dose, will be equal to or range from 0 to what? Tau. Okay? So the same thing that you know, and again, because we are using dust ratio, so by default, I'm talking about superposition principle, and by default, we are talking about linear kinetic, which means that the kinetic of single dose or one of the doses is not affected by previous doses or subsequent doses. So I can use the kinetic of single dose to predict the multiple doses kinetic. Okay? And this is the profile that we have for multiple doses kinetic, rather than what we have again, because this is the um, your profile for a single dose. So the same thing will be here with just multiple doses. You are not waiting for full elimination of your drug. Again, we are taking the second dose before the full elimination of the drug. That's why we have the minimum concentration at each dose increasing with time as a result of that. And we have the maximum concentration is, again, this is the maximum concentration increasing with time until we reach a point in which we have the steady state. And again, at steady state, we have input that is equal output as before. And again, we have Cmax at steady state that is identical. And we have C minimum at steady state, which is identical too. Okay, equal each other. One of the major differences that we know, or you should know it by, again, common sense, that again, before we had Cmax at time equals 0 in IV bolus and C minimum at time equal tau. And here, Cmax will be at Tmax for each dose, right? This will happen at Tmax for this dose, this will happen at Tmax for this dose, and so on and so forth. So it's not at time equals 0 anymore. And C minimum, it's as before, happens at the maximum time of that dose, which is tau. So this will happen at Tmax, okay? And this will happen at time that is equal tau. Okay, so this is the concept, is a sketch of the profile or the equation of the profile that we have. Again, from here on, you are just, I will ask you only about the details that I will just mention. Okay, we are interested again in the concentration of that the attained concentration at a steady state or at infinity time. And again, according to the definition, we said that if we are talking about steady state, then I need to have this as infinity, right? So we need to change this and this in two of the dust ratios to infinity. When we do that, this will be 1 and this will be 1. So this will be the equation of the concentration at a certain time, whatsoever the time at steady state. Okay? Again, at a steady state, we are interested about Cmax and C minimum, right? As before, we are interested about dose concentration and dose concentration, because those what we are concerned of to determine if I'm within the therapeutic window or not. So we need to determine T max or T prime max or T steady state max. I need to determine steady state concentration T max. Okay, and to determine so, we need to know when the rate of absorption equals the rate of elimination, but at steady state. And again, the rearrangement and the differentiation is already there in your textbook. But to make the story short, to determine the T prime max or T steady state max, we need to use this equation. Again, if you remember, this is way complicated compared to whatever we know about the T max for a single dose, right? If you remember, or you'll go back to T max determination of single dose, it was equal to ln K over K over Ka minus K. So the whole term here is added, okay? And again, if you remember, we said that increasing the complexity of the model will increase the complexity of the equations, and we'll need more experiments or data sets to be performed or examined. Okay, so first of all, to determine the concentration at steady state, you need to determine Tmax at steady state, and then accordingly, you will just substitute Tmax in the time. And again, you can use either this equation or rearrange it to shorter equations, and you will have both of them. Okay, you will have the general one and you will have this. And for sure in the exam, you will use this because it's shorter, so the margin of error will be less. Okay, for C minimum at steady state, again, steady state means that I need to add n equal to infinity, which we did just a couple of seconds ago, and minimum, which means that I need to have time equals to what? Tau. So the same as this equation, this is your equation at steady state. You need just to have infinity, which we already did it here, and we need to have t as tau, okay? When you substitute t as tau, you will have this equation, and again, we have tau and tau, so all the time that you have in the equation as tau. Okay, for the average plasma concentration at steady state, the same definition. It's not the max, it's not the minimum, it's not the arithmetic mean of both of them, it's not the geometric mean of both of them. It's the concentration. When you multiply it to the dosing interval, you will have the integration from 0 to tau at steady state. The only difference that you will have compared to IV bolus that we need to take into consideration the bioavailability. So just that is added to your equation that you already know. Again, steady state, average steady state concentration will depend on the bioavailability, the dose of the drug, tau of the drug, which is dosing interval, volume distribution, and K, or the total clearance or systemic clearance. And again, if you are talking about same dose given, the same conditions that I wrote for you, the same drug, linear kinetic, same pathology, same individual, same physiology, you will find that mainly this factor that would affect. And again, if we increase tau, which is making tau longer, okay, it means that average steady state concentration will be less by common sense, right? And we did this for IV bolus. And if the tau is shorter, which means that we are giving the drug more frequently, then the concentration at steady state will be more because we are not giving enough time for my drug to be eliminated, okay? And again, we said similar kind of things for IV bolus. So the concept will, or the concepts will stay as they are. There's no much differences. Okay, the only difference that you need to add the bioavailability of the drug. Okay, and again, it's the same as the concentration at steady state, average steady state concentration, the same concept as we said. You can use either 0 to tau at steady state or 0 to infinity for a single dose, which again giving me the same results, only the difference is F or bioavailability, which again give us the benefits of using one single dose kinetic to determine the target concentration that we need by changing the dosing interval, as I just mentioned in a second or in a minute ago. Okay. For the drug accumulation, we know that we had different ways of measuring the drug accumulation in IV bolus. The same thing is here, but as the Cmax is complicated as equation, we will use only C minimum at steady state versus C minimum for a single dose. The result will be 1 over this term, which if you compare it to whatever that you have in IV bolus is the same, okay? The same as you know from IV bolus. This will be under certain condition. One, that we are talking about rapid absorption of the drug, and each subsequent doses is administered in both a post-absorptive phase of the preceding or subsequent doses. And this is usually the common case. Just to say it again or paraphrase it. This equation is true once we are talking about rapid absorption of the drug. So the absorption of the drug is not a rate limiting step as we have in sustained release drug, because it's slowly absorbed. So we should have rapid absorption. This is one. And two, we need to have each dose is given in the post absorptive stage of the dose before it, which means we have this, and I'm giving the dose here. For sure, we are not giving the dose here. We are not giving the other, the second dose or the subsequent dose here, which is again for almost all the multiple doses we are giving the drug in post-absorptive phase. Okay. But if we don't have any assumption, or we are talking about slow absorption, then we need to determine the accumulation to have one term that is related to elimination and another term that is related to absorption. Again, because we can't assume that the absorption is rapid, and so we can't ignore it. Now, so if I asked you to determine the accumulation for rapid absorption or under this assumption, you can use this. If not, and I asked you to do that either with no assumption, which is the general equation, or for slower absorption, such as sustained release product, then you need to use this. Okay? For the number of doses required to reach the certain fraction of a steady state, again, if you go back to this slide, it's similar to the slide that you have for IV bolus. The same equation is true to be used if the absorption rate constant is larger than the elimination rate constant, which is usually, as a rule of thumb, 10 times or more difference or fold. Okay? And this way, we can use the equation that we already have, either this or that, for that we already have in the IV bolus. Okay? Again, you can use the same thing under this assumption. For the loading dose and maintenance dose, the same idea. When you have a loading or you want to give a loading dose, C maximum for the loading should equal the C maximum to reach the same steady state concentration of the maintenance. C maximum of the loading should be equal C maximum at steady state of the maintenance. C minimum of the loading should be equal C minimum of the maintenance at steady state. So the same thing, if you want to have the ratio of loading over maintenance, it will be equal this term, okay, which again is similar to the accumulation under the assumption that we are talking about, again, rapid absorption, and the drug is taken for each doses, it's taken in the post-absorptive phase, not before it. If we can't do this assumption, you need to add one term that is related to elimination and another term that is related to absorption. Okay? And for, of course, this is usually the general case as we talked about the accumulation. Let's talk about this profile, which can be an example of a lot of extravascular and oral drugs. We have concentration versus time to 4 different profiles, okay? If we consider this as a loading, so D star is your X loading, okay? And D as the constant dose of the maintenance, which means that we have different profiles of different cases of loading doses, okay? If the loading over maintenance equals 1, which means that we don't have any loading, then we start to increase the loading dose compared to the maintenance dose, 1.5, 2, and 3. Okay? Let's notice a couple of things. One, whatsoever the profile, the loading dose that we are using, if it's lower than the steady state, this is your steady state concentration. If it's lower or higher, at the end, we will reach the steady state concentration, Cmax and C minimum. And it's similar to whatever you have in your IV infusion, if you remember. It could be higher, it could be the same, exactly the same, or lower, okay? But at the end, you will reach the steady state. Another thing, if you think about which one of them as a profile is the best or the targeted, or what we the desired, let's say the desired loading dose or profile that we need. We said the desired or targeted or whatever that you are aiming to have, that we have the steady state concentration directly. If you go through the profiles, you'll find the best profile to be at steady state directly as this one, okay, in which my loading is twofold the maintenance, okay. So if I ask you which is the best profile, is the third profile, in which the loading is twofold of the maintenance dose. Okay, and this is what you find usually in oral, some of the oral drugs. Let's say some of the antibiotics, you'll find either the physician will tell you at the beginning, take 2 pills or 2 tablets, and then take 1 tablet per time or per tau. Okay, or you have it in the package insert that the first dose is taken as 2 tablets or capsules, and then take 1 each 8 hours. This is the thing that it's giving you a loading dose and you don't know about it. That is, we are reaching the loading, the steady state concentration directly. Okay, again, those kind of things are true if usually when the tau is near the half-life of the drug. Okay. And by this, I finished the, let's say, the summary of extravascular, and I will do just the calculation of this question to finalize the extravascular multiple doses regimen. Okay.